At the beginning of this chapter, we learned to draw pictures of vectors and to even draw them to scale and find out what happens when we add several vectors by putting the tail of one to the head of the other and finding the resultant vector. In that situation, remember, we were trying to find the length or the magnitude of the vector and its direction, which is the angle that it's at. I'm just going to put here theta, the angle. So then in the next section we developed the meaning of components, and we even talked about a situation where if we were canoeing down a river and we were going with the current, that the speed of our vehicle, our boat, plus the speed of the current would be our total speed. Yet if we were going against the current, we would have to subtract the speed. We'd have to take the speed of our boat and subtract the speed of the current because we'd lose ground because the water was trying to push us backwards. So now what we're going to do is we're going to use components of vectors and the Pythagorean Theorem and the trig function tangent to find the magnitude and direction of a resultant vector in any situation, whether or not the vectors are at right angles to one another, which is easier, or not. So let's go ahead here. So find the magnitude and direction, in other words, the angle from vector, let's see, from vector A for the resultant. So what I'm going to do is I'm going to draw a picture of this, and vector A is a bit longer. So let's go ahead and draw vector A about 600 units in length. Just going to the right just because I'm kind of thinking about the rectangular coordinate system, so I'm going in the positive x direction. And then let's draw vector B. They're at right angles to one another. I don't know if that's going to work. Let's see. Sorry about that. So here's vector A, and here's vector B, about a third of that length, supposed to be at right angles to one another. Again, A at 592 units in length, and vector B at 195 units in length. And remember that to find the resultant vector, we go from the tail of the first to the head of the last, and I'm just looking for this value called r. So you can see, because of this right triangle, that I can use the Pythagorean theorem to find the magnitude of r. Now you could use your program, but I'm just going to take 592 squared plus 195 squared and take the square root of that, and I would get 623.2. I don't have any units on this, so I'll leave that alone. The next thing I need to know is I need to know the size of this angle. I'm going to call it theta. And remember that the tangent of theta is defined as the side opposite over the side adjacent. Or also remember it's defined as y over r. But we've got this side opposite and the side adjacent. So now to find the size of what I call my reference angle, but in this case it is the actual answer, I'll take the inverse tangent of 195 divided by 592. Make sure your calculator's in the degree mode. I'll just go ahead and do this really quickly. Second tan of 195 divided by 592. Oops, I'm sorry. So second tan of 195 divided by 592, and that will give me the 18-degree angle. And I'm all set. So 18.2 degrees. This is my solution to this problem. It is magnitude of 623.2 at an angle of 18.2 degrees. Let's quickly, with respect to A. So I'm going to go ahead and say that as well. So let's go ahead to this next one. So vector A is shorter this time, 1,795 units in length. Vector B is more than twice as long, so I'm going to try to do this. And then the resultant is from the tail of the first to the head of the last. So again, here's vector A at 1795. Here's vector B at 3715. I draw this picture so you can really kind of see how long the red line should be. You know it's going to be more than 3715, maybe 4,000-ish, maybe in the vicinity of a little bit more than 4,000. So we're just using the Pythagorean theorem, and we get 4,125.9. And then to find theta, we're going to take the inverse tangent of the side opposite divided by the side adjacent. Again, I'm going to note for you that this is the angle called theta, and that turns out to be 64.2 degrees. And to describe my answer, I have to not only give the magnitude, but I have to give the angle, and I have fully described this vector quantity. Okay, let's look at the next piece. So let's say that now I find that I have a set of components, x and y components, in the rectangular coordinate system. So let's go like this. Let's draw the x-axis and the y-axis, and in this particular problem the x component is 89.5, but the y component is negative. So I'm going to draw this in blue. So x goes to the right 89.5. This time I'm going to put their tails together, and so the y component goes downward a negative 52. I'm going to let that be about my negative 52. Here's my x and my y component. I'm going to draw that parallelogram idea. Remember that this side right here is the same length as this side, and my resultant vector is from where their tails are together to the opposite side of the parallelogram. So that's the solution that I'm looking for now. So I want to find this, and I'm just going to drop this line way over here. So I'm going to drop that over here and just remind you that this one is 89.5. and this one is 52 units in length, but the negative got me into the fourth quadrant because my y component was negative. But nonetheless, when I go to solve for the r value, I'm just going to take the 89.5 and square it, and the 52 and square it. I don't need to put the negative sign in because a negative number squared is positive. So please don't put it in, because if you don't put that in parentheses, it's going to give you an incorrect answer. I have the length of that red line is 103.5. Next, what I want to find is the size of this reference angle. And I'm going to use tangent again because this is the side opposite and this is the side adjacent. So please, this is just a right triangle that's sitting in the fourth quadrant. So I'm going to say that my reference angle is found by taking the inverse tangent of 52 divided by 89.5, and I can tell that's going to be less than 45 degrees, so I kind of should be thinking about that, and that gives me a 32-degree angle. And so finally, do recall that when we represented the trig functions in Chapter 8 in the four quadrants, that if I wanted to name the size of this angle from the positive x-axis in a counterclockwise direction and stop right there, that I would go all the way to 360 and subtract this reference angle. So remember that theta in the fourth quadrant is equal to 360 degrees minus your reference angle. So 328 degrees. So here's the several ways I could write this answer. I could say that my resultant, its magnitude is 103.5 and its angle is in standard position a 328-degree angle. But you know this 32-degree angle? Remember that if you go clockwise to describe an angle, you can call that a negative 32 degrees. So you could say it's at an angle of a negative 32 degrees. Or let's say it was aviation, it was a plane. You could say it's at an angle of 32 degrees south of east, because the x-axis is east, and this is south of east. So there's another way to say it. I don't care, you know, what way you say these. Don't forget you got to have your 103.5 on here, but I don't care how you describe the angles. Let's do the next one and just talk about its location. So in terms of the rectangular coordinate system, In this problem, x is negative and y is negative. So x goes to the left, 740. I'm going to make that one kind of long. And then y goes downward, not so long. Let's stop right there. And then let's go ahead and put the arrowheads on these two vectors and draw our parallelogram. And so the resultant of this problem, sorry, I didn't put the straight line tool on, that's okay, is found by, let's use the 740 here, don't care about the negative sign, the 276 here, because I got this in the third quadrant, because x is negative and y is negative. So by the Pythagorean theorem, if you would take 740 and square it, and 276 and square it, you would get, I'm afraid I might not have that one, so let's go ahead and do it on the calculator. So 740 squared plus 276 squared, and then I'm going to go second square root, second answer to take the square root of that previous answer, so 789.8. So 789.8. Don't forget to find my reference angle. I'm going to use tangent because I know my x and my y components. I'm looking for this angle right here, this reference angle. So I'm going to take the inverse tangent of the side opposite over the side adjacent without any signs on it so that I can get an acute, something between 0 and 90 degrees. Second tan of 276 divided by 740, and I get the reference angle is 20.5 degrees. And then now don't forget here, in this case, if I want to represent it in standard position, from here I go 180 and I add that 20 degrees. So to find an angle in the third quadrant, I take this, again, 180 degrees plus the 20.5 degrees, which is 200.5 degrees, and I would describe my resultant as 789.8 at an angle of 200.5 degrees. I could say at an angle of 20.5 degrees south of west. I can even describe it as this about 160 negative degrees as well. We'll now next, after this segment, we're going to look at two vectors that are not at right angles to one another. Much different problem.